Hello everyone, this is Shri Guru over here. Welcome back to my YouTube channel. Today we are going to solve some numericals on the basis of photoelectric equation. Look at the first one. When a light of wavelength 400 nanometer is incident on the cathode of a photocell, the stopping potential is recorded as a 6 volt. If the wavelength of the incident light is increased to 600 nanometer, calculate the new stopping potential. Here, the two wavelengths are given, but at the same time, he asked to calculate the stopping potential for the second wavelength. By using the Einstein photoelectric equation, we can calculate. But if you properly observe the problem, the work function remains the same for both wavelengths. Therefore, first we will calculate the work function using this equation. H nu equal to phi naught plus EV naught. Here phi naught is a work function and EV naught is the kinetic energy of the ejected photoelectrons. First we will calculate the energy of the incident photon by using the equation Hc divided by lambda. Here the first wavelength 400 nanometer is given. Substitute this value into this equation where h is a Planck's constant. The value of Planck's constant is 6.62 into 10 raised to minus 34 joule seconds, and c is a velocity of light, that is 3 into 10 raised to 8 meter per second, and wavelength is given, that is 400 nanometer. 400 into 10 raised to minus 9, because nano is 10 raised to minus 9. After the simplification this, we will get 4.97 into 10 raised to minus 19 joules. Similarly, by using the same equation h nu, here we have rearranged the equation for the work function. Phi naught is equals to h nu 1 minus EV naught. Already we have calculated incident photon energy. Here 4.97 into 10 raised to minus 19. And E is a charge of an electron, that is 1.6 into 10 raised to minus 19, and V naught is given here 6 volt. I have written here 6. After the simplification, this term we will get minus 4.63 into 10 raised to minus 19 joules. Similarly, for the second wavelength 600 nanometer, first we have to calculate the energy of the incident photon of energy h nu naught by, as we did in the earlier, the equation hc divided by lambda to 6.62 into 10 raised to minus 34, 3 into 10 raised to 8 divided by 600, nano means 10 raised to minus 9. After the simplification, we get 3.31 into 10 raised to minus 19 joules. Similarly, EV naught 2. For the second potential, he asked you to calculate h nu 2 minus phi naught 2. Phi naught already we have calculated here. Substitute in this equation. The phi naught we got minus, in terms of minus of minus, here plus, that is 3.31 into 10 raised to minus 90. It is incident photon energy, plus 4.63 into 10 raised to minus 19, that is work function. After the simplification, we got 7.94 into 10 raised to minus 19. If we take this electron magnitude value charge in the right side, then it goes to denominator, that is a 7.94 into 10 raised to minus 19 divided by 1.6 into 10 raised to minus 19. After the simplification, we got 4.96. This is the stopping potential for 600 nanometer wavelength of light. Look at the second problem. A monochromatic light of frequency 6.0 into 10 raised to 14 Hz is produced by a laser. The power emitted is 2.0 into 10 raised to minus 13 watt. First, A. What is the energy of the photon in the light beam? Second B, how many photons per second on an average are emitted by the source. First, he asked you to calculate energy of the incident photon. E is equals to h nu, where h is a Planck's constant. We know this, 6.63 into 10 raised to minus 34 joule seconds, and he is given frequency of the incident light, that is 6.0 into 10 raised to 14 hertz. After the simplification, we get 3.98 into 10 raised to minus 19. Energy is measured in terms of joules. Next, he asked you to calculate how many number of photons are emitted by the source in 1 second. Therefore, if P is a power emitted and N be the number of photons emitted by the source in second, and E be the energy of the photon. Energy of the photon is already we have calculated here, and power is given, that is P divided by E, that gives the number of photons emitted. 2.0 into 10 raised to minus 3 watt divided by 3.89 into 10 raised to minus 19. If you simplify this, we'll get 5.0 into 10 raised to 15 photons per second. This is the one of the simplest problem. Next problem, a light of frequency 7.21 into 10 raised to 14 hertz is incident on the metal surface. Electrons with a maximum speed of 6.0 into 10 raised to 5 meter per second are ejected from the surface. What is the threshold frequency for a photo emission of electrons? Solution: by using the Einstein photoelectric equation, half mv square equal to h nu minus h nu naught. If you simplify the value for v naught or nu naught, the equation become nu naught equal to nu minus mv square divided by 2h, where nu is given, that is 7.21 into 10 raised to 14 hertz, and m is mass of an electron, that is 9.1 into 10 raised to minus 31 kg, and velocity of the ejected electron is given 6 into 10 raised to 5 meter per second whole square divided by 2 is here, and h is a Planck's constant, 6.63 into 10 raised to minus 34 joule seconds. If you simplify this value, then we will get nu naught equal to 4.74 into 10 raised to 14 hertz. This is the threshold frequency of photo emission of electron. Next problem, a light of a wavelength 488 nanometer is produced by an argon laser, which is used in a photoelectric effect. When a light from this spectral line is incident on the cathode, the stopping potential of the photoelectron is 0.38 electron volt. Find the work function of the material from which the cathode is made. Here once again the Einstein photoelectric equation, EV naught is equals to Hc divided by phi naught. What we require? Phi naught equal to Hc divided by lambda minus EV naught, where H is a Planck's constant, 6.63 into 10 raised to minus 34 joule seconds, and C is a velocity of light, 3 into 10 raised to 8 meter per second. Lambda is given 488 nanometers 10 raised to minus 9. We have to convert this in terms of electron volt. Therefore, I have divided this equation with 1.6 into 10 raised to minus 90. And EV naught is given, that is 0.38 stopping potential. If you simplify this, you will get the work function in terms of electron volt, 2.17 electron volt. Next problem, calculate A, momentum, and B, de Broglie wavelength of the electrons accelerated through a potential difference of 56 volt, where these are the given terms. The first equation, EV equal to half mv square. If we rearrange this equation for the value of momentum mv, equal to square root of 2 EVM, where this V is a voltage and this V is a velocity. Substitute the values which are given here in this equation. 2 into E is a charge of an electron, 1.6 into 10 raised to minus 90, and volt is given 56 volt, and M is a mass of an electron, 9 into 10 raised to minus 31 kg. If we simplify this, you will get 4.02 into 10 raised to minus 24 kg meter per second. This is the momentum, and this is the first value. And next he asked you to calculate the de Broglie wavelength. De Broglie equation: lambda is equals to 12.27 divided by square root of V angstrom. Potential difference is given 56 volt. If we substitute in this equation 12.27 divided by square root of 56, after the simplification we get 1.64 angstrom. Thank you for watching my video. Don't forget to like and share and subscribe. Thank you.